Hello everyone, my name is Cheng. Today, I would like to talk about the impact of artificial intelligence in design education. More specifically, what would I like to go over is the study that me and my co-author did on how human designers could work with the AI technology to create a better product. Many people think AI could take over their jobs. However, we believe tomorrow's design would rely on both human and AI. To understand the future of design education, study its past is very important. Over the last decades, each technological paradigm shift often leads to an engineer education paradigm change. For instance, traditional engineer drawings use pen and paper. With the advancement of computational tools, engineers start to draw 3D models on computers. Further, with the help of AI, designers could use machine learning to improve their design efficiency. Perhaps in the future, designers' role would focus more on analysis than designs. So this may also change the future direction of design education. What we would like to investigate is, can AI alone generate superior design solutions than humans? Or can human and AI work together to achieve an even higher design efficiency for mechanical designs? In this work, the superior design solutions are defined as reducing the amount of materials, better structure stiffness, higher safety factor, and few parts of the volumes. To accomplish this, the method that we will use is called generative design and topology optimization. First, let's talk about topology optimization. It computes effective material distribution based on any given loading force, define design space, and design goals. Here's one example. As you can see, the volume differences representing the unnecessary mass. What is left in this picture represents the necessary materials to meet the product requirements and design goals. Topology optimization presents a whole set of a solution which wasn't conceivable by human designers. The next one is generative design. What this allows us to do is to generate numerous design solutions for a given design constraint. For instance, here's a seatbelt bracket in airplane. After assigning the given design constraints, the combination of generative design and the topology optimization algorithms would produce several results satisfying the same requirements. Designers could evaluate each design and select the best result. We have been able to come up with those designs for a while. However, the traditional manufacturing methods has their own drawbacks to bring those type of designs to realization. By using additive manufacturing such as 3D printing, those generative design solutions will soon be available for consumers. Ultimately, we will use those two methods to create a case study and show the differences between human and AI design, and how to teach future designers how to design a better product with AI. Little literature has shown us how to incorporate AI into design education. Instead, there are many instructions on how to use AI. For example, Autodesk provides their guidelines on how generative design works. After you collect product data and the constraints, the generative design software will produce a set of solutions for designers. This design iteration will end until designers finalize the product. So based on this procedure, we propose a more detailed flowchart for design education. Compared to the previous one, data acquisition has been separated into requirements and design constraints. This is important because requirement documents can be interpreted in different ways by designers. How to teach students to create various design constraints while satisfying the same requirements can be a critical step for product development. The second difference is that we include designers into this process. Designers have two major tests. First, select the best model from generative design and the finite element analysis. Second, designers should readjust the constraints to compromise the model performance for each design iteration. One of the main takeaways is Maybe educators should not only teach how to design in the future, more importantly, how to evaluate designs with different analysis should be the next step in design education. Now, I'm going to hand it over to Tulu. He will explain how to test this proposed design flowchart by using a case study.
We conducted a case study to assess the plausibility of what we consider to be the future workflow of engineering design, in which a human designer works in unison with a generative algorithm to produce a superior solution. This study will be presented in accordance with our proposed workflow, starting out with defining system requirements, then proceeding to the generative steps in which we, the designer, establish constraints for the study using Autodesk Fusion 360's generative algorithm, validating these generated models using finite element methods, then refining our constraints accordingly as part of an iterative cycle till an acceptable solution is reached. From there, we'll present the simulated structural performance of our final generated design and compare it to its initial cognitive counterpart. The case study was initiated by first picking a suitable cognitively generated model to use as a baseline. This would be used to define our system requirements. We chose to go with a bookshelf bracket due to its simplicity in form and function. The primary requirement of this commodity is that it must support a static load, and this is fairly easy to assess. Several different bracket designs were sourced from Amazon's online market and evaluated based on total mass and maximum load capacity. Two typical attributes a designer would work toward when designing such a commodity. The scatter plot shows the variation in these two attributes on multiple designs we came across, with some designs being more aesthetically oriented and not so efficient in that they had a high mass but supported lower loads than alternative brackets with lower masses. These can be seen in the red region of the plot. Other more efficient solutions can be seen in the green region, and some which were very robust at the top right corner of the plot, which lay on the interface between the red and green regions. We decided to go with one of the more efficient designs in the lower left corner of the green region on the previous slide, and modeled it in a CAD environment to act as our cognitive baseline. This was a spatial truss bracket seen in black on the left of this slide. Our study, test 1, placed a vertical load of 40 pounds on top of the bracket indicated by the blue arrows to simulate the weight of books and the wooden shelf on the bracket. The bracket also has fixed constraints on 3 fastening points indicated by the gray lock icons. These constraints were used as part of the baseline initial conditions in our generative design setup, visible on the right side of this slide. Here, the designer is responsible for setting the constraints for the generative algorithm to carry out the study. These include 1. Fixed geometrical features, which are features the AI has been instructed not to modify, seen in green as fixed geometries. 2. Setting regions to prohibit material during generation of the model. This is all geometry in red. And 3, applying the loading conditions and fixed constraints to initiate the generative study. A total of 3 generative studies were performed to come to a viable solution. Test 2 had the most input from the designer. Test 3 gave more freedom to the algorithm. And 4 gave the most control to the algorithm with little to no input from the designer. A chart illustrating the level of topology optimization and cognitive input on each test can be seen at the bottom left-hand corner of this slide. Looking at the figure on the right, I would like to point out any gray geometry is inactive and will be ignored while the algorithm is generating the design. Each generative study, test 2 through 4, yielded a wide range of possible solutions for the designer to choose from. The models displayed on this slide are but a few of the total solutions proposed by the generative algorithm. Test 4 shows 2 non-converging solutions which indicate an incomplete optimization of the design. From a design engineer's perspective, regions marked here and here show some geometry that looks more susceptible to fracture under load in a practical scenario. Test 2 and 3 yielded fully converged models that appear more robust and seem more equipped to handle practical loading applications. Besides structural intuition, These two models fared well when evaluated using finite element methods that created the same loading conditions in the cognitive spatial truss in test 1, displayed on the previous slide. After conducting finite element analysis on the generative models, test 2 was selected as our generative model of choice. The subsequent slides show how the structural performance compares with that of its cognitive counterpart. Maintaining the material properties and loading conditions from the cognitive design in test 1, the generative approach produced a more efficient design which exceeded the target minimum safety factor of 3. This was achieved with a mass reduction a little over 50%. The top plots displayed in the middle and to the right of the slide show the maximum von Mises stress and minimum safety factor of the cognitive design respectively, while the bottom plots show attributes on the generative counterpart. We observe that the generative algorithm, guided with the judgment of a trained designer, has produced a design that results in a lower stress, inherently increasing the safety factor of the bracket and using a fraction of the material. We believe this study has shown that our proposed workflow is a valid approach to engineering design practice moving forward, and that a generative agent can assist designers to produce superior solutions within a few minutes, something that could traditionally take days, weeks, months, or more to realize, if at all. Our proposed workflow establishes that a human component is required to guide and validate the generative design tool. The advent of these tools suggests a paradigm shift in engineering design, prompting students and professionals to become more proficient in interpreting design constraints, modifying design constraints to suit the system requirements, and applying good engineering foresight to assess practical solutions from those generated by the algorithm. This inherently indicates a paradigm shift within the educational structure of engineering design. Moving forward, we anticipate more rigorous research to facilitate the efficient implementation of generative solutions into the engineering design curriculum. Though the study we conducted provides insight to the possible direction of engineering design, it still begs the questions: how will the future of collaborative design with AI components evolve? Could we reach a point where AI could solely manage the engineering design task based on system requirements alone without any input or guidance from the designer? That is to say, can we fully automate the design process? And if so, what are the implications for the role of the design engineer in tomorrow's industry? It would be prudent to state that these ideas will play a crucial role in establishing another evolutionary step forward in the development of engineering design practice and education. Thank you for your attention.